Alright, welcome back. In the last video, we were doing an example of a regression on LSD concentration. Yeah, that's right. So hopefully you're not taking LSD while you are taking the test this week, but if you are, you can use this model to kind of like figure out how good you'll do. Okay, so in this video, we're going to do a quick example on what we saw in the very first example of these videos this week. But we're going to take a little bit of a deeper look in it just so we can kind of see what's going on. So here is the deal. A physiologist wants to know the relationship between muscle density and age. They recruit 60 volunteers between the ages of 41 and 78. Now that's a big deal. Okay, 41 and 78 are the range of our values as far as the age goes. Okay, so keep that in mind. And then they record each person's muscle density. Using the following information, let's figure out the relationship between these two things. Okay, so muscle density and age. What's our outcome? What's our outcome? Nice. I really do feel like Dora the Explorer sometimes. Our outcome is muscle density. And then what's our density? What is our predictor? Nice. It's age. Very good. Very good. Proud of y'all. Okay, so we got that. We're all good. We got our ages here, 41 to 78, so we'll keep that in mind too. All right, so first we'll plot our data, right? And so what do we say? We have 60 volunteers, right? So there should be 60 dots on here. And it looks like there are, so that's good. And then we plot the dots first, and then we get the computer to draw this line. We're drawing this line. Pretty cool. Pretty easy. All right, so already, just like in the last one, we can see that this is a negative relationship already between age and density, okay? Whereas age goes up. Let me do this. Age goes up. Density goes down. Okay, so we got that. Now we just need to then figure out the equation for this line, and then we got to figure out if that line can be trusted, if the location of that line can be trusted by the intercept, if the relationship between these two variables can be trusted, right? The slope, the kind of rise over run situation, right? From way back when. We got to figure out if we can trust this whole thing that we're saying here. Okay, so we move on, and then we get our model output. Okay, so we have the residuals here, 5-number summary this time, and already I think I mentioned this in the first video too. We've got some symmetry going on here where we're close to 0, close-ish, and then it's -6 and 6. That's pretty decent. And then as you go further out, you're getting a little bit more inconsistent. You know, this is 23, and the minimum is -16, so that's not going to be. It might be a little bit skewed in some way, but otherwise, this is only to catch your eye, right? If you see something big going on here, then you got a problem, right? But for right now, I think this is okay. And then we have our coefficients table here, where we're pretty familiar now, where we've got our equation for a line. Looks like that. And what's what? Well, the intercept is the beta naught, and then our slope here, it's just right there, beta 1, right? And this is our predictor, okay? Very, very cool. Now, can we trust these two estimates? Well, we'll start off with the age. Can we trust that the relationship for every 1 unit increase in one thing is density going to change by this much? Well, we just come over here to our p-value, and they are both very statistically significant, right? So already we know that we can what? Can we predict and can we relate? Well, we can relate because our p-value for the slope coefficient only is statistically significant. We can trust that this is a close estimate of reality, okay? And then we can also predict because we have this as statistically significant, the slope is statistically significant, and the intercept is also statistically significant, and that's seen right here. Sweet. Okay, very cool. So we can relate and predict. Woohoo! Sweet. Awesome. Okay. And then we have our sort of everything we don't care about except for this right here, which is good. Okay, so now let's see if we can trust the overall process, right? We already have a good hint that we probably can, but let's check the residuals. Let's see if we're doing any major over or underestimation, and we'll look at that as a histogram, okay? And that looks something like this, okay? So we have our scatter plot that we're used to seeing, right? Already we can tell that our data are pretty linear, right? Ignoring the line there. Everything here is pretty consistent. You got a little something out here, but that's not a big deal, right? I don't think that's too big of a deal. So everything here is behaving pretty linearly, pretty consistently, which is great. Okay, so that's that first assumption. Our second assumption here is, I would say that that's decently met. We have a little bit of an outlier, and I think that's what this is corresponding to, right? Where we have that positive residual, that's what this is representing. We do have some residuals out here that are a little high, right? If we were to kind of zoom in here, trace down, right? This point on the line is big time underestimating the reality of where that data point would show up, right? And I think that's what's showing up out here. So already, we'll say that the distribution here is decent. We'll say that it's decently normal. It's not perfect. Our line isn't doing a perfect job, but we don't really expect the line to do a perfect job. We just want it to do more or less of a mediocre job, and I think that it is, which is fine, which is great. Okay, very cool. So we can trust everything in here. We can trust everything here. The residuals are not too bad. We're not doing a whole ton of over and underestimating. Just a little bit here in this sort of area. No biggie, though. No biggie. Okay, so then we got to interpret this mother, okay? So we'll come in. So what is it? Well, we'll just recall here. Let's write out the whole thing. So it's density. Okay, and I need my intercept first. It's muscle density. I need my intercept first, so that's 156.35, we'll say. Okay, and then what else? Well, our intercept is there. We need the slope, and the slope is negative, so that's negative 1.19, right? This is all familiar. And then x, age in this case. Very cool. Okay, cool. So for every 1 unit increase in age, if we were to increase age from 50 to 51, it's going to change this whole thing by this much, okay, by that much. So for every 1 unit increase in age, every 1 unit increase in age results in a 1.19 unit decrease in, and then what's our outcome? In muscle density. In muscle density. And that's the relationship between these two variables, right? Between these two variables, which is pretty sweet, I think. So for every time we increase age by 1 unit, by 1 year in this case, every time we increase it by 1 year, the whole story is going to change by 1.19. By negative, it's going to decrease by negative 1.19. Okay. All right. Very cool. We can relate. We can predict. Can predict since okay. Very cool. So we can relate and predict since the p-value is less than 0.05 for both beta naught and beta 1. I think I did have a small aneurysm there. There we go. So that's all good. That is okay. We can trust the model because we have decent model residuals. See how convenient this is when you don't have to do it by hand. It's all here for you. I think that's great. And this is what you'll see in real life too, which is wonderful. So let's answer some questions. Okay. What is the estimated muscle density for someone who is 65 years old? Okay, so we can write that out again. So we'll say MD, muscle density, equals 156.35 minus 1.19. And what do we plug in? Well, we just plug in 65, right? So get out the old handy-dandy calculator. I will. Okay. And it is 156.35 minus 1.19 times 65. Very cool. Okay. So our muscle density, and let me just make sure that, yeah, cool. Our muscle density would be, I can't remember the units, and that's okay, would be 79 units, we'll say, just 79 units. Very cool. All right, and that we can kind of confirm that too by coming over to our trusty dusty scatter plot. I'll erase these again. Cool. So I said 65, right? I said 65. So that's like right here. Boop. And I'm going to come up, and I'm going to come over. Very cool. Right, so what did we say it was? 79 something? Looks like we're just right about there, which is wonderful, which is super, super great. It's going to be off just a little bit, but, that's okay. We're only drawing here, only estimating. So that's all good. That kind of makes sense. It's a good way to double check, right? So our predicted value, our estimated value for someone who's 65 years old is a muscle density of 79, okay? What is the muscle density? What would the estimated muscle density be for someone who's 18 years old? Okay, well, here's the deal. We could go in here and plug this in. We could plug in 18 here instead of 65. But do we have data? We don't even have data for people who are younger than 40, right? So there's no way on God's green earth that we'll be able to say anything about the behavior of people who are less than 40 and their muscle density. And the same thing for people who are, I guess, are like 80, right? That's about where that is. We just don't know, right? We have no idea. It likely probably kind of curves downward, right? You get probably something like that, maybe, but we don't know. We can't do any sort of extrapolating like that because we just do not have that information. So that's, again, just like the last one. Whoa. Cannot answer. Actually, I'm just going to say no. We can't extrapolate. Very, very cool. And then, just like the last one, how much of the story is being told here as far as muscle density? Well, all we want to do is just come down here to the r squared. The r squared, not worried about the adjusted r squared, but we just worry about this one. And what is that? Well, let's see. Age explains 75% of 75.01, so we'll just leave it as that. Explains 75% of the variance of muscle density. Very cool, right? So that's the whole idea here, is that we're trying to see how good our model is at explaining the overall variance of our outcome. In this case, it is muscle density. And if we were to maybe add something in, which we're not in this class, that's multiple regression. But if we were to add in another variable, likely that is going to tell more of the story, which is sweet. I think that's very cool that we can do that. So we've got the regression equation written out there. Everything can be trusted. The model looks pretty decent. We've got a lot of the story being told by this one predictor, age, which is great. We can say that as age increases, as you age, it is likely that your muscle density will decrease by negative 1.19 on average, at least. So that's okay. And that's pretty much that. It's so convenient when it's all given to you like this, and you don't have to do a whole ton of math, right? So I'll probably have one more example for you after this, and that'll be that. So the test will have everything that we've done pretty much with inferential statistics, which is sweet. So with that, I will see ya when I see ya.